Okay, let's practice. Let's get as much of pages 52 through 56 done as we can. Asking lots of questions, working through things together, talking them out, trying to figure out what strategies are going to work. Knowing that sometimes there's a couple different ways that could work, but there's usually a best way. Of course, direct substitution, always when I think of factoring, dividing away problem. Factoring helped me split up fractions. Looking for those two limits, right? If you get stuck and there's nothing else we can do, we try looking for that sine of theta over theta or the 1 minus cosine of theta over theta to see if we can isolate that so we can just take that limit, because the limit of a product is the product of limits. The limit of a sum is the sum of those separate limits, breaking things apart in ways that allow me to just think about one piece and then the other and see where it gets me. Okay, I have all of the solutions, so I'm happy to flip and turn and talk through and work through anything that you want. But it's really going to be to your benefit to do as much of this at first on your own. And then if you get stuck, then we can talk about it. Okay, so same thing for you lovely folks at home. Ask questions, work through these things as you go. If we need the weekend to finish, great, but you might be able to just get it done right now. That'll free up your calculus weekend, so that's never a bad thing. And then we go from there, okay? So let me know what I can do to help, of course. Talk to each other. Or do like I do and just talk to yourself. Whatever works for you. This is the best kind of practice that you can get in class, where you can ask questions, you can look stuff up, we can work through it together. Whatever you need, you just let me know. Okay, time is yours. Use it as wisely as you can. Let's see if we got everybody here today. People are probably still online, which is good. Dan, does this say the number 2 on your desk? Cool. Making sure I got everybody in their spots. Yeah, sure, absolutely. Awesome. So whenever you're ready, let's talk. Or if you just want to say, hey, can you scroll to number 7 so I can see the answer? Whatever we want.
Mr. Rosengren?
Yeah.
Can we look over number 1 on page 54, please?
Sure. Okay. I'm glad. I think this is page 54. Yeah. I'm very glad that this came up early so that I can highlight some things that are going to make your life a lot easier. When you think about the 2 trig limits that we proved over the last couple of days, the sine of x over x and the 1 minus cosine of x, what was the limit? What was the x or the theta value that we're getting close to in both of those limits? 0, right? Is that going towards 0? Then don't try finding those limits. Those only work when x or theta is going to 0. If you're going somewhere else, don't go looking for either of those 2 limits. Try some of our earlier strategies, like identities, factoring, dividing away the problem, something like that. And so that was the first thing that initially really stuck out for me, as I said, oh, theta's not going to 0. I am not looking for sine of x over x or sine of theta over theta or 1 minus cosine of theta. I'm just not going to look. Okay, well, what else can I do? Well, I can at least hope to get this function that we're taking the limit of from 2 different trig ratios, cosine and sine, down to just 1. Because usually that'll help me simplify. But if you have a mixture of sines and cosines or tangents and secants, and trying to get everything down to just one trig function is a great way to start. Well, how can I do that? A nice little Pythagorean identity on top. The great thing about those monomial squared terms for sine and cosine is that when you make the switch from one to the other, you will always have difference of squares, which is always factorable. Now, of course, plugging in pi over 2 would have been a great way to start. So I always kind of think about that first, but I would get 0 over 0, so the limit exists. But the number does not, right? We're undefined at that spot, but the limit should exist, so I should be able to find it somehow. So little Pythagorean identity on top. Factor difference of squares. Divide away the problem. Once the problem is gone, direct substitution. Yeah. Well, on page 56. That is a good one, for sure. What's the first thing to try every time? Direct substitution. Just plug it in. Now, I will be the first to admit that I did not catch that right away. I looked at 12, and after doing, a dozen and a half, 2 dozen examples where I had to try something else, my autopilot mode kicked in, and I was like, okay, what can I do to this fraction to make it work? And so I got really messy with it, and that still worked. I was still able to get it to do what I wanted. Direct substitution, way easier, but let me show you what I tried. It was super gross, but really, really fun. I know those two things are usually mutually exclusive, but what was it? I'm gonna drop the limit just for the sake of writing this out, but it was that, right? 1 minus tangent over sine minus cosine. So no squared, so there's no identities like that I can use. Binomials everywhere, right? And so in my mind, I'm like, oh, maybe I'm dividing by 0. Let me see if I can eliminate that problem. So I focused on the denominator, thinking that direct substitution wasn't going to work for whatever reason, so I just didn't think it through. And so what I did, a really good strategy, and again, please don't do this if direct substitution works, but my idea was to multiply by the conjugate, hoping things would then magically be amazing, multiplying by the conjugate of the denominator, both top and bottom. And you're going to see that, oh my gosh, geez, this is going to work, I think, but it is not fun. I know, that was really nice. I'm going to come down here because I cannot stand it. Okay, so I multiplied out the tops, multiply out the bottom. The denominator is really nice because it's multiplying by conjugates, so I can get to there. That's cool. And then I figured multiplying out the tops might be to my benefit. I just wanted to see what would happen. But I rewrote that as sine over cosine, hoping things would just kind of cancel as I went. So take this and multiply it by that. So 1 times sine was sine. 1 times cosine was cosine. Sine of theta over cosine of theta times sine of theta. Oh, sorry, negative. So this is minus. Sorry. Minus. This is where things started to get gross. Sine squared over cosine. Here's where things did work out a little bit nicer. Sine over cosine times cosine. The cosine's cancel. So minus. Again, this is way more work than I really needed to do, but something nice happened, so that at least that happened. Those went away. Okay. And so again, denominator for the time being is not changing. But then I looked up top. I said, okay, one of them's not a fraction, the other one is. Let me try to put those together by creating a common denominator and then just making one big fraction out of it. So like I needed to turn this into a fraction with cosine on the bottom. And so what I did is I multiplied top and bottom by cosine. And what that gave me was a fraction, once I combined them together, all over cosine, that was cosine squared theta minus sine squared. You see that? I'm just trying to save myself some steps of actually writing it out. But like I multiplied this top and bottom by cosine of theta, cosine squared, over cosine minus sine squared over cosine, so I can put them together one fraction. Why do that? Well, a fraction divided by something, this now is a factor of the bottom. So I have cosine squared theta minus sine squared theta over cosine of theta times sine squared theta minus cosine. Again, there's a limit in front of all this all the way through. I'm just saving myself a little bit of time. Are these two factors exactly the same? No, so they don't divide to 1. But they are exactly opposite. So these divide to -1. Now, just for good measure, I'll bring the limit back in. Where were we headed? 0?
Yes.
That was brutal. Brutal, brutal, brutal. And I was like, man, that's pretty, well, so in my mind, I was like, oh, I did it. That was cool. But then I said, well, wait a minute. Hold on a second. Cosine of theta, like cosine of 0 is just 1. And so I backed the truck up and I was like, well, wait a minute. What was my denominator from the beginning? It wasn't just sine of theta, which was the 0 part. It was sine minus cosine. Let me just plug in 0 and see what happens. And of course, I get -1. I get the same answer. But I'm the first to admit that I tried that long, crazy way separately off of this page because I did not know where it was going to get me. Like a lot of these problems I can just look at, like I know the best way to do it. Why? Because I have been doing calculus longer than you've been alive. My first calculus class started in 2002. That was my senior year of high school, 2002. 02, 03. I'm an 03 graduate. I know. Feels like forever. It was. High school is just a blur at that point. It really is. But a good one. I learned lots. Made some friends. Have some regrets. Living that life. So, very long-winded story short. Plug it in first and see what happens. But it doesn't happen often, right? A lot of these limits, they're not just going to keep giving us direct substitution because I'm not going to learn anything from just plugging numbers in over and over and over again. But they do like to sprinkle it in from time to time to see if we like kind of fall into that autopilot mode that I absolutely fell into. Okay, I have to change the function. Got to change the function. Got to change the function. Well, hold on, slow down. Check it first, right? Take 10 seconds of your life and see if you can save yourself 10 minutes. Because I tried, first time around, I didn't multiply out the top. I left it factored and got nothing out of it and tried the Pythagorean identities. You should see the scraps of paper floating around this room that just end up in the recycle when we try stuff out. Failing and then backtrack. That's calculus. Sure.
Could you go up to 9 and 10?
Sure. Absolutely. So these rely on some pretty important things to remember. That if you can isolate constants, so the 1 there, the 3 there, they can come out. Of these two very specific limits. How much time do you have? why can the constants come out? It has to do with the relationship between the sinusoids that exist on top and their relationship to how the unit circle opens as we open up angles within the unit circle, and we compare those within a rational function. So it's really about the fact that the whole for these functions exists at 1 and exists at 0. And when we talk about things that your middle school teacher probably skipped, but taught you, just didn't maybe say it, was the multiplicative and additive identities. That multiplying by 1 doesn't change anything and adding 0 doesn't change anything. We call those the multiplicative identity and the additive identity. Multiplicative, multiply by something, doesn't change. Add by something, doesn't change. And the fact that we are multiplying by 1 right here, that buried within this limit are some constants. And the constant that is going to be multiplied through theta is a change to the frequency in sine. But sine of 0 is still always going to be 0. And so when I mess with the frequency, that point doesn't change, right? The starting point of sine doesn't change. And then same thing for cosine, right? That function always starts at 1. And so when I do 1 minus that, I'm back to 0 again. Now, the big thing that you'll probably notice with these functions and using these two limits is that they will mess with the frequency of sine, but not of cosine. And that's because I can start it at 0 compared to starting at 1. And it's a little bit harder for me to, like, we're not really, like, it's not really being factored out. We're recognizing that the starting point doesn't change. And so we're being very informal, skipping a lot of the behind the scenes stuff that's true and saying, oh, like, here's step A, I want to get to step Z. I'm not going to show you B through Y. I'm just going to jump to Z knowing that all of that is still true. Mathematicians in the 17th and 18th century did all the proving of that for us, and we're trying to save ourselves some trouble. So that's the long and short of it a little bit, is that we're messing with frequencies by multiplying something through theta. You'll see that this would not work if we mess with the phase shift. It's never going to be sine of theta minus pi. Can't do it. It just doesn't work that way. So these are very, very specific trig limits. Sine of theta over theta and cosine of theta. And like the graphs prove it, and like it's just a little bit beyond how far we've gone with trig and the relationship of trig functions and their inputs when we make them into a ratio and see what happens. There's just more advanced calculus happening there that we just haven't got to. Yeah, I don't, terrible answer, but hopefully you just start believing. When we get to chapter 2, you will learn the strategy behind why it works, but we will not explore that level of complexity with functions like that. The proof for just sine of theta will probably take me both of those boards in this one, and we'll do it. So sine of theta over theta, messy, but it's a good one. But that's like March, like that'll be like the end of March. We'll get to that. Maybe before that, we'll see. We spent a month on chapter 1, so hoping we can do the same with chapter 2, chapter 3, and chapter 4, and there we go. There's calculus. Calculating.
Mr. Rosengren,
Yeah,
can we go over number 4 on page 54, please?
sure. Recognizing something we wrote previously, and I'm just going to pick letters, but if you have constants being multiplied through A times sine of B theta over C times theta, very informally, but it does work out, the A, the B, and the C can be pulled out, leaving behind a limit that we know is 1. And so basically, we can skip all of that conversation and say, oh, there's a 2 here, there's a 3 here, there's a 1 there. Let's just look at that ratio, the product of those constants on top over the numbers.
Okay, thank you.
But this is what's happening. So feel free to write that as often as you want, but that's all I'm doing. I'm taking out the constants, multiplying them together, seeing what happens, and knowing that because that last little limit is going to be 1, nothing's going to change. Uh-huh.
Go over 11 on 56.
11 on 56, sure. I'm just going to give anybody a second to write that down before I switch, but let me take a peek. Oh, okay. What's theta going to? What's the limit theta approaches? Not 0, right? So I'm not looking for the sine of theta over theta or the 1 minus cosine of theta. So it kind of like takes that option out, which leaves me with just more algebraic strategies rather than like weird calculus limit isolation strategies. So that's kind of the first thing I always want to look for is, okay, which independent value am I trying to get to? If I'm going towards 0, I have a couple more options. What, number 11? Yes. Oh, going the wrong way. No, is that right? Yeah. And so I wish I could plug it in, but I can't because I would be divided by 0 because cotangent of pi over 2 is cosine over sine, which is 1 over 0, so that's even undefined, right? And so I just tried to think about ways to simplify that fraction. And eliminating that fraction to start is a good idea. And so instead of dividing by cotangent, I rewrote it as multiplying by the reciprocal of that, right? Dividing by 2 is the same thing as multiplying by 1/2, right? You can change, flip, copy, dot, plot, whatever you want to think back to like when you first learned to divide fractions. I'm going to rewrite it instead of cosine over cotangent. Let's do cosine times the reciprocal. Because every function has its reciprocal in trig, which helps us eliminate or at least rewrite fractions. And now that I've gotten rid of the initial fraction, let's see how we can simplify. Well, nothing's squared, so Pythagorean identities go out the window. And so I just try rewriting things in terms of sine and cosine to see what goes away. Cosine goes away. And usually when we like rewrite or factor and divide away something in common, usually we're dividing with a problem, right? And the problem there was dividing by cosine. Because cosine of pi over 2 is 0, right? Go to pi over 2, the x value is 0. I just divided away. So now I just have the limit of sine.
Okay, so the pi over 2 is how we know that, like, we would go to tangent instead of like cotangent could have been cosine over sine.
Right. So yeah. Let's say we have this kind of initial thought. Cosine of theta, of course, limit, right? I'm just saving some time. Cosine over sine. Right, that's so cosine over sine. And if I tried plugging it in right now, if I just plugged in pi over 2, I would get, okay, cosine of pi over 2 is 0 over 0 over 1, which is 0 over 0, which is under pi. But it's 0 over 0. There's a hole, which means the limit exists. So there must be something that I can do to find the location of that hole somehow, algebraically, analytically, isolating certain things, doing something to get me to that spot. So I had that initial thought of, okay, like what happens? Plug in pi over 2 and see what happens. And so it didn't work in my favor to actually try direct substitution. So let's think about how to rewrite it. Now, if you wanted to, you could have thought about it like this, like cosine of theta over 1 over cosine of theta over sine of theta, right? Complex fractions. And then, but the point in doing that is to always rewrite the complex fraction as a product to see what happens. Most will go away either way. So whatever thought process you use, you'll get to that same spot of sine theta. Just how you want to go about it. And for me, with basic versus reciprocal trig ratios, I always kind of use those to my advantage. I'm not going to divide by cotangent, I'm going to multiply by reciprocal. I'm not going to divide by cosine, I'm going to multiply by secant. I'm not going to divide by cosecant, I'm going to multiply by sine. And just kind of using those relationships. Every function has its reciprocal to help me rewrite it in a way that just allows me to see like cosine over cosine. Like I didn't notice like cosine over cotangent. I don't see what can cancel. Like visually in my mind or even on paper, I don't see it. So I rewrite it so it becomes visible.
Okay, thank you.
This 14? Okay. We'll do 14 first. This was gross. And I'll tell you what, this was not my first try at this one. The first thing I tried was I tried expanding it. I tried multiplying everything out. Just to see what would happen, hoping things might cancel, right? And so, like, I had x plus 3 cubed minus 8, right? All over x plus 1. I'm going to save myself some time. So all over x plus 1. So I just tried to see what happened if I could multiply that out. So that's x plus 3 times x plus 3 times x plus 3. And you could do it the long way and like actually distribute, or you could use Pascal's triangle with binomial expansion. 1, 3, 3, 1 for the x plus 3 cubed, right? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Those are my coefficients. And then I still have that minus 8 at the end there from that last one. X to the third, 3 to the 0. X squared, 3 to the first. X to the first, 3 squared, x to the 0, 3. Okay, x cubed plus 9x squared plus 27x plus 27 minus 8. Now this is, I think, the long way to do this. Because what happens is, like, so this is just my numerator, right? This is all over something, this is all over something, this is all over x plus 1. What happened is, once I tried simplifying this, like, I know the issue is plugging in -1. I can't do it. What's that, plus 19? Right? And of course, the limit in front of all this, I'm just, again, saving space is fine. I'm like, okay, well, now what? I do not see that cubic as being quickly factorable, like factored by grouping, or like I don't see it. But if I plug in -1 from the beginning, or right here, I get 0 over 0. So the limit exists because there's a hole, so it better be factorable. I should be able to write it as x plus 1 times something over x plus 1 so I can divide that away. How the heck do I figure out what that something is? Well, what's a good way to factor polynomials if you know what one of the factors or one of the zeros is? That's what I did. Bring down the 1, crisscross, zigzag, multiply, add together. Zigzag, multiply, add together. Zigzag, multiply. Add. Okay, cool. At least it works. So x squared plus 8x plus 19. And then those divided away. Then I could plug in -1, and I got 12. I was like, man, that's a lot of work. If this thing, if this from the beginning worked out to be that, and that was factorable, that must have meant that this is also factorable. It's the same thing, right? This is the same as this, which is the same as this, which is the same as that. And so I backed up and I said, well, okay, do I recognize something about this setup as being a special case where it is factorable? So I looked at that setup and I said, ooh, okay, x plus 3 cubed. That's a perfect cube. It's a binomial. I don't like that it's x plus 3. I wish it was just x. But it's not. It's x plus 3. But it's still being cubed. And 8 is 2. That is the difference of perfect cubes. Where this is a cubed minus b cubed. It's just that a is x plus 3. A, b, a squared, a, b, b squared. That's how we factor the difference of perfect cubes, right? Same, opposite, always positive. Now that's tricky to see, especially with the binomial, to be able to say, okay, like, all right, a, there's a again, right? The whole x plus 3. But it works, right? A minus b, a squared plus ab plus b squared, because it will factor it for you, which is what I liked about it, because then I could just divide the x plus 1 away, and then I just have what's left behind. And this, that's x squared plus 8x plus 19. This is buried in there somewhere. But I don't need to expand that out just to be able to get a version that I can plug -1 into. Tricky for sure. Upper level kind of question that takes a lot of foresight into realizing what you're sitting with. Like, how do I do something with this? Well, what am I going to do first? I'm going to plug in -1 and see what happens. Plug in -1, 0 over 0. And that lets, it's like a beacon of hope. Like, okay, I must be able to do something. But what the heck am I going to do? And I think both choices are great choices. Expanding is probably more work, but it's less brain power. I just multiply it out, put it back together, see what happens. This was a little more analytical, like recognizing structure, knowing how to factor the difference of perfect cubes. They love the difference of cubes, sum and difference of perfect cubes in calculus, because it just takes upper level factoring skills to do that. And so those kind of questions come up. But multiplying it out is always an option. But I had to like multiply it correctly, which gets sloppy if you're doing it the long way. But it can be tough with Pascal's triangle, my own expansion, and remembering how to do that. And then you get to something that is not obviously factorable, but it has to be. If I'm getting 0 over 0, it has to be that. And then, if it's factorable, how do I want it to factor? It's got to have the same factor as the denominator. It's got to be x plus 1. So the 0 had to be -1, so I could use synthetic division. Oh, yeah. So that was a tricky one for sure. That's why it's number 14. Right? That's why it's at the end. They're usually pretty good about putting usually a good collection of more complicated ones at the end. But look what they did right before that. They gave us a little sneak peek of what we could do. Right? They were like, hey, remember difference of cubes? Remember that? We can do that, right? And then they push us just a little bit. So I really like that 13 and 14 were side by side. That's why when I got to 14, my mind went immediately to difference of cubes rather than expansion. I was like, oh, I just did that. Ooh, look at that. But again, a lifetime of calculus practice under my belt helps too. Here you are with a month of calculus practice under your belt. So, yeah.
Could you get a 6, 7, 8, 9 on
Start with 6 and 7. Can't look at all. Tricky. These are good examples, though, of the kind of things that, oh, I see it going to 0, a denominator of just theta or just theta squared, just something like that. That leads me towards kind of looking for those perfect limits, those two, not theta with theta and 1 minus. The first one is factoring, so I break it up with multiplication. Second one is addition and subtraction, so that's how I break it up. But these are hard. They really are. These are not easy by any stretch. Until you've done hundreds and hundreds of these kind of examples over years, that's when they start to feel easier, when you start to know what to look for. And that's okay. We're not going to master these necessarily as a class collectively all at once. But we don't have to. We really don't. This is just a small portion of what we'll need to be able to do a week from today when we take that chapter 1 test. And I'll get you more practice, middle of next week. We'll have some downtime to kind of get you ready. I know I said this kind of virtually to you guys yesterday. You guys sit in front of me. But rather than have us rush to an in-class test Wednesday, Thursday, when we're kind of strapped for time, or have some people take it at home and some people take it here, I didn't think that was equitable. For this chapter 1 test, we'll just take it Friday at home. I'll send it out, and you can just get it done at your leisure with as much time as you need. Kind of similar to what we have in the past, right? I'll send a link to a Google form. If you don't have to show any work, great. Just type in your responses or select the right multiple choice or click as many check boxes that are true. And then for questions like these, I'll just have you handwrite it out and put it up on Canvas. But you'll have 20-something examples under your belt with these trig limits, and I'll ask you to do like 2 or 3. That's it. And we'll go back to like the regular graphs and regular functions and just evaluating limits that way, and factoring to simplify, rationalizing to simplify. So like leaning on your quiz 1.1 for guidance as to the kinds of questions for the first half, that's what I'm going to do. I'm going to look at that quiz and ask very similar kinds of questions, and then I will just add some trig. And then Monday's thing, we'll talk about the connection between limits and continuity a little bit more formally. We'll kind of formalize that on Monday, and then see if we need a minute on Tuesday to just kind of practice those ideas. And then like review Wednesday, Thursday, and then test Friday. And this way we can start chapter 2 Monday, March 1st. Sure. I like this page a lot. This is 4 great questions about the 2 kinds of things we can do to isolate those 2 special ones. Connected by addition and subtraction, connected by multiplication. Recognizing that if it is a sum, the denominator has to be the same. But if we break things up with factoring and we have ourselves a product, we can break the denominator apart as well. However we see fit, whatever is going to be the most useful. Yeah. Sure. I'll wait a minute so we can get the like with this one with number 8, like initially I wanted to cross out the thetas and the cosecant of thetas, but I had to pause for a second and realize I couldn't do that yet. Like, oh, they're so similar. Like the top and the bottom of number 8, they're so close, but I can't divide them away yet because it's not factored. It's not isolated as one, common fraction. So I just made it. I was like, oh, okay, I'll just do that. I will break up that single fraction into 2 and see where that gets me. And nice, that first fraction just divides to 1. And then kind of like what we were talking about, Grace, me and you before, we were talking about like dividing, instead of dividing by cotangent, we multiply by tangent. Instead of dividing by cosecant, let's multiply by intercept. And so kind of the in-between thought to have with number 8 is that I can like rewrite it like that, right? Don't divide by cosecant, let's multiply by sine. And then it just appears on top. Instead, multiply through by that 1. And oh, look what magically appears. It's amazing. Sine of theta over theta, there's my limit. Why do I care about searching for that limit? Because theta is going to 0. If that was going to anywhere else, I would never care to look for that specifically. Okay. Which one, Noel? So that's probably this. Again, single denominator, that monomial, x going towards 0. There's my clue. I'm looking, if I can, to try to isolate the sine of x over x kind of setup. I have things being added on top, so I will break that into 2 functions, 2 fractions being added. And I'll just see what I can do with those limits separately. All right, first fraction, sweet, the x's divide away. There is me dividing away the problem, and now it's the limit of a constant, so my answer is just that constant. And then with this one, like the 3 up top, the 1 on the bottom, so they come out. I didn't write this, but that's kind of what's happening there, right? The sine of x over x is right there. That's just a 1, so 5 plus 3. So if you want to write that step in red, that's never a bad idea. But those limits we can start to work through a little bit faster if we start kind of recognizing what I talked about at the beginning. Just out come the constants for that limit specifically, the sine of x over x. You can see they didn't talk about that one with the 1 minus cosine of x. It doesn't quite work the same. And Peyton and I, during the second period at the end, we started to look at what happens. Let me show you this here in a second. Oh, yeah, we have it up there. You can't see the function though. Like what happens when we start messing with some of those numbers? You start messing with the frequency, it is not going to give you the kind of limit like I was supposed to go to 0. No, now I've got an asymptote at that spot instead because I've messed with the frequency of cosine. Now, the problem that looked like this one had not right there, right? Had the 3 in front as an actual constant that I could then just factor out, right? Oh, 3, 1 minus cosine of x all over x. Cool, those are the same functions, so I can find the limit of that, no problem. By pulling that 3 out, but put a number, you can change that to a 1. Start messing with those numbers, maybe we get lucky. Maybe we get lucky. But we start adjusting that number in similar fashions and things start to change. And so we can't quite rely on that as much as we would like to. This is a pretty funky looking function. Let's start messing with the frequency. Looks pretty cool. Yeah. That's what's great about these periodic functions. You can make really cool designs of it. Yeah, a little bit more freedom with the sine one than we have with the cosine one. You don't have to because it's piecewise, but it is a good one to practice with just to familiarize yourself with the ideas behind dealing with limits of piecewise functions, where the x value that we're approaching is the spot where the one function stops and the next one begins, right? When this number is the same as that one. Because if that was just as, hey, as x approaches 0, well, it's just the top function. Like that piece is just right there and I'm good. Or as x approaches 12, oh, that's just the bottom function because 12 is bigger than 3. I'll just plug it into the bottom one. But if you're taking the limit of a piecewise function at what I like to call the break point, right, where one function ends and the next one starts, you have to kind of consider what happens as you approach 3 from the left and approach 3 from the right. And if you're approaching the same value from both sides, then the limit exists. And clearly, the function is not defined at 3. Neither of those inequalities is less than or equal to or greater than or equal to. So there is definitely a gap somewhere. But is it a removable or a non-removable discontinuity? That's kind of the question. So that's what I did. I did 3 things. At first, I checked the limit from the left. I said, okay, what's going on there? Well, the limit from the left, so where is x less than 3? Right there. Top one. So I just plug it in. And I want to check 2.9 and 2.99 and 2.999. That whole one-sided limit was just to help us figure out what's happening at an asymptote. That was going, like, am I going up towards infinity because my answer is positive? Am I going down towards negative infinity because my answer is negative? This is wondering, I mean, look at the top function. It's just quadratic. There's no asymptote there. There's nothing wrong with that. I can just plug it in and see what happens. That function on its own is defined and continuous everywhere. So plug in 3. Let's see what happens. Oh, okay, I got 9. All right, so that's my limit from the left. So as I travel along this piecewise function from the left, I'm going to go up to 9. And then separately, let's check the limit from the right. Okay, well, numbers that are to the right of 3 are bigger than 3. So which piece of my piecewise function has x bigger than 3? Oh, the bottom piece. Okay, let me plug in 3 into that function and see what happens. So 8 minus cosine 3 pi over 3. Okay, cool. I got 9. Last thing I do is compare them. This number was the same as that. From the left, I'm approaching 9. From the right, I'm approaching 9. So my limit exists because my left and right side limits are the same. If those numbers were different, the limit does not exist and I'm done. If the limit does exist, that's because the left and the right side limits are the same and they're equal to some real number. Okay, cool. Therefore, that limit is. And we could try looking at it. I don't really know how to do piecewise in here. Let me see if I can do it. I don't know. Yeah, they don't like that notation like the calculator does. I don't really know decimals, piecewise notation all that well. But like there's the whole function. What was it? 8 minus cosine of pi x over 3. So imagine that like this purple function stops right there. So like this part doesn't exist, right? And from the right, we have this function here, and then none of that exists to the left. Right? So what we've got is we've got this gap within the functions, and what we want to see is, okay, what happens as the purple one approaches x equals 3, and what happens with the black one as x approaches 3? Are we approaching the same spot? And we are. There you go. If and when you get this done, just put it up on Canvas, homework 1.5. If you need the weekend to finish it, please take it. Go ahead. But get it into me before midnight on Sunday. But if you've gotten it done, wonderful. You can post it anytime, and we will be good to go. And I will see you Monday.
Thank you.
You're welcome. See ya. Let's get Squishy back in his home. Was he happy? Did he have a good time?
Yeah, you did.
Oh, good. Nice.
We're gonna have you-
Hi. Did you have fun? You trying to climb on me? 1.5.
I have a work.
I have today every weekend.
No, I finally got it. Oh. This is my last question for now. Don't be a problem. I'm not gonna say.
So how we do? How we feeling?
Yeah.
Got like 80% confidence.
Yeah.
Pulling around that range. That's pretty good at this point. That's pretty good. That's pretty good at this point.
Yeah, just we did so many different examples. Like.
I know. It's like, you want like 5 examples of the same thing, and then 5 more examples of the same thing, like right in a row. That's not how this class works.
Because I just started getting the hang of it, and then I got to this page, and that was just it. 56.
Yeah. Oh, that's the last page, and that's where the hard problems are always going to be. Usually, what they do is they kind of, and it's a potpourri for sure throughout with different kinds of strategies, but they save the trickiest ones usually for the end. Which is kind of like the style of the SAT. Like within a section, the harder questions start appearing more towards the end. And, that'll kind of be the same thing with the AP, more or less. I mean, you guys obviously don't worry about that, which is nice.
Yeah.
But I mean, think about next year, Calc 1. Right, that's where your calculus is going to start. But the good news is that you are doing the first half of that first semester with me, which is limits and then derivatives. We'll talk. Once we get to chapter 2 and we learn what a derivative is, that's all we do. Once we learn the shortcuts for derivatives, we never do limits again. Limits are happening in the background, but we know all the shortcuts, and so we can just use those shortcuts. And then we get more complicated, and the shortcuts turn into long cuts. What's up, Peyton?
Yeah. Thank you.
Yeah.
I'm just finishing downloading.
Go for it.
I'm trying to figure. I messed up my picture, so I'm like,
Oh my goodness. Oh, I don't care. You don't have to put them necessarily in order, but I know it makes my brain happy. I'm sure it makes your brain happy too.
Yeah. Makes it easier for you to grade.
It does.
I guess I'll be nice.
Okay, I like that.
I guess I'll choose kindness.
I like that. Mr. Burton, what's going on, brother?
Fire.
Yeah, me too. I don't know. It is lunchtime. Oh, we come to homeroom? Yeah. Yeah, so we have lunch.